So we're gonna solve that for this series. So let's go with J to the J. Then Sn is the sum J from 0 to n R to the power J. So try to find the formula for this. Okay. I don't know why this doesn't work. So final formula, you can derive an explicit formula for this sum. So please try to do this. Or if you know this already, you can tell me. Anyone knows the formula for this sum? So this comes from the following formula. I don't know if you know this. So if you have two numbers and AB, then A squared minus B squared, you can write this as A minus B times A plus B. And, A cubed minus B cubed is this. And you can guess the formula for in general because just from this. So now you would have all the terms, all the product A, K, B, L, and K plus L is 3 now. So you start with A3, and then you get A squared B, AB squared, and B cubed, and so on. And similar formula in general. So you start with A cubed, and then you reduce the power of A increase the power of b, so a square b and ab square and then b cubed. And the reason that you get exactly this is because you see when you multiply out this guy give you a to the power 4, and then this multiply with this give you minus b to the power 4, and then the rest can be put in pairs that cancel out. So for example, if you pair this with this, you get the minus sign that's going to cancel with this times this. And similarly, if you pair this with this, you get minus a to the power ab cubed, then it's going to cancel with this product of these two. Or if you want to, you can just multiply this out, and you would get a to the power 4 minus a cube b plus a cube b plus a square b square ab cube, and the minus b times all this gives you minus a cube b minus a square b square, and then minus b to the power 4, which is the last one. So you see all this guy cancels. And from this, you can easily see that a similar formula exists for any power here. So if you have a n, let's say a n plus 1, then this would be so this can be written as a minus b times is a minus b, and you start with a n minus 1b, and then finally a b n plus b to power b to the power n minus 1. Okay. Now, in particular, if you put a equal to 1 and b equal to r, then you get this. So a equal to 1, so all this become 1, and then b equal to r, so you start with this. So first term going to be 1, and r, and then r squared, and so on. And now you divide both sides by this factor, then you get exactly the term that we want to, the partial sum Sn. So you get this equal to Is this clear? Do you have any questions? Okay, now to find the series, what you need is to find the limit of this sum. And the limit of this sum is, you should note that the limit of this sum is 1 over 1 minus r, because this is a constant, doesn't depend on n. N is a thing that we push to infinity, and this thing is a constant independent of n. And you get this. And we have seen earlier that the limit of this r to the n exists if and only if r is between -1 and 1. So this exists if and only if you have this. By the way, this formula only works for it's not 1. It's very important, because at this step you can only divide this if this is a non-zero number. And you can see that when r equal to 1, you have very easy formula for Sn, which is as n plus 1. Right? So we only have this, but we also during the proof of this, you also shown that the limit of r to power n is 0 if the absolute value of r is less than 1. And the only special case is when r equal to 1 here, and the limit of this would be 1. And if r is bigger, the absolute value of r bigger than 1, then certainly the series, this sequence doesn't converge, because its size goes to infinity. Okay, so come back to this series, then this is equal to 1 over 1 minus r if r less than 1. And we also shown that when r is bigger than 1, then the series doesn't converge. So so we have not only this, but if r is bigger than 1, then because when r bigger than 1, then the limit, this limit doesn't exist. That implies that the series diverge. So lim Fn doesn't exist. Now the one special case where we cannot use this formula here is when r equal to 1. So if r equal to 1, then Sn goes to infinity. So the series diverges as well. So that's finished our proof of the formula for the geometric series. Do you have any questions? Okay, so let me go back to the slide and give you the formula. How do I? So we just saw this formula. You multiply with a, then you get the series is a over 1 minus r, and when r bigger than 1, and of course a is non-zero, then the series diverges. Now this formula, the way to remember this formula is that a is the first term, and r is a common ratio. So you have first term divided by 1 minus common ratio. But this is very important that you remember the common ratio is the next term divided by the previous one, not the other way around. Otherwise you would get into trouble. So do remember this. Okay, so let's do one example with this formula. So let's see if I can maybe I can write here enough space. So compute this series. Okay, you apply the formula. As a 3 and then 2 power 2 plus 1. So please try to compute this using the formula and let me know your answer. Are you finished? Okay, please try this so that you understand the formula. Okay, let's see. Okay. Yeah. Actually, you don't have to split into to two parts. Even though the signs are alternating, you don't have to group them into odd and even terms. So let me show you how. Yes, all you need to do is to check that it is a geometric series. That is the ratio of the next term uh, over the previous terms are always the same. And then you use this formula here, which is easier to remember. So let me show you. So we have the series 3 to the power 2n plus 1. So let's call this an, and we have to work out this ratio, and that is first to increase this by 1 because that is an plus 1, and then you're going to divide by the previous terms. And this is quite easy, right? So if you divide the numerators, you're going to get minus 3, and then you divide the denominators, then you get 4. So this is a number that is independent of this n. So that shows that your series is geometric series. So this and this is your the common ratio. And so this by our formula, this is simply a2, which is the first term because our series start with n equal to 2, divided by 1 minus r. Now a2 is simply 9 over 32, right? And then you divide by 1 minus 3 over 4. And I believe that give you 9 over 56. Is this clear? Do you have the same answer? Okay, very good. Okay. So usually geometric series is when you saw this kind of thing, constant to some power, and then the power can be 2n, 3n, and so on. But if you have powers like this, you definitely get some geometric series, and the only thing that you need to do then is to find this r. And very importantly, you have to figure out the first term correctly. So these two give you the value of the series. So the moral of this series is when r is less than 1, the terms go, getting small very quickly. So they add up to some constant in this case. Whereas if r is bigger than 1, then the series go getting less very fast. And so the sum getting fast very quickly, and they diverge. So let's continue. Okay. So let's come back, and so telescoping series is the series that we saw earlier, this series. And whenever a series, the terms of the series can be written as the difference of consecutive term of another of a sequence B, then that sum is called a telescoping series. So this example you have already did at the beginning. And this is a something called a telescoping series. But you can also have something that is not strictly like this, but you can still sum the sum, right? So let's do this example, see if you can. So let's say n equal to 2 to infinity 1 over 2n plus 1 and 2n plus 5. Can you try to do this? So try to do the same thing as we did for this series. So like this, you see you split into two parts like this. Then you will see that this one is not strictly, this one here is not strictly a telescoping series, but you can still imitate this and find the sums. So in this case, it will not have this formula here, down here. It's only work for strictly the telescoping series like this. So please try to compute this, okay? Anyone finished? Anyone finished? Oh, what is your answer? Okay, let's see. So this one, you can write this as, I'm not sure if that, yeah, maybe that's correct. So this is 1/4 of n 1 over 2n plus 1 minus 1 over 2n plus 5. And so this is 1/4 of, if you write down the series, you will see it is, it starts with 1 over 5, and then minus 1 over 9, and then 1 over 7 minus 1 over 11, and so on. 1 over 9 minus. So you see it is not strictly a series of this form. And so on. Because see, the first term is 1 over 5 minus 1 over 9, but the next term is not 1 over 9 minus some things. And so it's kind of two telescoping combined into one like this. So, but you can still see that there's a lot of cancellation going on, and there is a formula for Sn. But let's not do that. Let's quickly compute this. So you have cancellation here. This and this cancel, and then this and this, and so on. So the 15 gonna come next here, and then it's cancel with this one, and so on. So every term's gonna, if you look at the infinite sum, everything cancel, and you left with this and this. And finally, the sum of the series is so 1 over 4 times 1 over 5 plus 1 over 7, that is 12 over 35. Yes. So this is the final answer. Very good. Do you have any questions? So this is not quite strictly a telescoping series, but you compute it in the same way. Okay, so let's see what is next. So let's talk about some properties of series. So one thing that we didn't do is questions. Okay. So this is a very basic criterion that if you have a convergence series, then it must be true that the terms of the series goes to 0. And hence, if you have a series where you saw that the terms doesn't go to 0, then the series diverge. And we already use this, for example, in the geometric series before. We see that if r is bigger than 1, then certainly the size of this is always bigger than 1. So that implies that this is not true. So this is not, does not hold. And that, by the second part of this theorem, implies that this series diverge. The sum of Rn diverge. So this is very simple criterion that is very useful. So sometimes it's by just looking at this, you can see that if you know that this doesn't hold, then you can conclude that the series diverge. But if it does hold, then you cannot say anything. So this is very important point. So if you don't have this, then if you don't have an go to 0, then the series diverge. But if you have this, then it doesn't imply nothing. It's imply nothing. Because if you have this, the series may diverge or it may converge. And it's essential that you notice the direction of the arrow. So this implies nothing. But what implies is that the series converge. If a series converges, then the term go to 0. It's not the other way around. So this doesn't imply that the series converges, okay? You already saw that, for example, you look at the P series, and these are very different series, right? Even though the terms of each series go to 0, 1 over n go to 0, 1 over n squared go to 0, but this one diverge, but this one converge. So this is something that we saw earlier. Okay, so let's do this example 3.3. So this you already know the diverse, right? So which one of the two converge? These two here. Have you finished? Is there any series in these two series converge? So try to see whether the terms here go to 0 or not. If the term doesn't go to 0, then the series diverge. If it does go to 0, then you have to do more work. Yes, both of them are divergent because you do not have so the absolute value, so let's call this an, then remember an go to 0 if and only if the absolute value of an go to 0. But in this case, you have this. So let's say n is bigger than. Shouldn't. This is. Let's do this. So the lim of the absolute value of an is this 2/5, and you can see that because this one is very small compared to this one. So these guys are the main terms here. The 2 to the 2 times this part and this part are the main term. The dominating terms in the numerator and denominator, and when you divide them and take the absolute values, you get is equal to 5. So it doesn't go to 0. So that implies that an doesn't go to 0. For the second series, you can kind of see that. So very often the cosine takes some value that is not close to 0. So for example, so this would be so pi to pi 6. So this may be 6 here, and so let's say 1, 2. So and 1 is here, 2 is here maybe, and 3, say 4 and 5, 6. So you see that there is many value of the integers close to this, very close to number of the form k times pi, where cosine has absolutely 1. So it's rather big. And you can, so let's see how quickly can you see this. So pi over 3. Yes, so what you can do is, let's look at this band. So there's other ways that I'll show you later on. So let's look at this circle here. And so you start with n equal to 0 here, 1, 2, 3, 4, 5. So you just go round every time you increase by 1. So what you can do is you look at this this range here. So this is pi over 3. So you look at this part of the circles. So the angle here is pi over 3. This is another pi over 3, and the same here. And you just notice that on this 2 arc, if n lies in here, then the cosine is quite large, right? So in here, the absolute value of cosine x is, if x is on this 2 arc, going to be bigger than a half. So it's not close to 0 at all. And you should notice that the length of each of this arc is 2 pi over 3, which is certainly bigger than 1. And so you know, the n must be frequently lies on this 2 arc. So let's say n lies here. So this is n, then n plus 1 must be inside here. It cannot jump over this all the way to this down here, because the length here is bigger than 1, right? So very frequently n has to lie on this 2 arc. and so cosine doesn't go to 0. Or another way, maybe easier for you to understand, is suppose cosine does go to 0. So we're gonna get contradiction out of this. Then cosine of 2n, which is the sequence, the same sequence, but we only take out the even terms, must go into 0 as well. But this one is 2 cosine square minus 1. And this, if you have this, then this go to minus 1. So this is a contradiction. Is this clear? Do you have any questions? Okay, let's continue now. So we have a couple of easy. We have to prove this, right? So let's see. Okay, I will prove this. Before that, let's finish with a couple of simple properties of the conversion series. That if you have two conversion series, you can add them up, and you can subtract them, you can multiply them with a constant. So we all do this. We do this already. So let me just so for example, if you have this series times 1, let's say n from 2 minus let's say 2 over n, then you can compute this, because you realize that this is a combination of two conversion series, so you can split it into two parts like this. And the reason is they are of very different nature. The way that you compute them are not the same. And here you can pull even the constant out, but it doesn't matter. You can pull the 2 out here if you want to, but leaving it inside is okay as well. So tell me, what is this the value of this series? Have you finished? Anyone finished? Okay, let's see if it is 1/6. So you compute this the same way as before, and let's give you the first term, so 1/2, and then you get 2/9 divided by 1 minus 1/3. Yes, so this is is that equal to 1/6. Okay, any questions? Okay, let's now prove the theorems. So now we have to show that if you have a convergence series, you have sigma an, let's say start with 1, you can start with anything, imply that an goes to 0 as n go to infinity. So the terms go to 0. And all you need is, so let's say this, if you know that it's converse, then that is equivalent to the partial sum converse to the value of the series. So L is exactly this sum as n go to infinity. So can you deduce from this this one, how to deduce? From the fact that Sn converges to L, so Sn is A1, A2 plus An converges to L. Why does this imply that Ans go to 0? Anyone knows how to deduce from this fact that an go to 0? So actually it's not difficult, and we solved this maybe a couple of times already. So you have limit of Sn equal to L, and if you shift the index by 1, then you also get this, right? So this implies that the limit of Sn minus Sn, the difference of these two sequence is 0. But this is just exactly an. Is this okay? And do you have any questions? Okay. All right. Let's continue then. So we have one test already that can tell you. So this test is out. So besides the two type of series that you can explicitly compute, telescoping series and geometric series. So these are the two type series that you can compute. We know one test. So this test here that allow us to conclude a series diverge. So without having to compute the explicit formula for the partial sum Sn, because that would be impossible in this case. But if you are in the situation when an go to 0, then as I mentioned earlier, you can not conclude anything. If it doesn't go to 0, then the series diverges. But if it does go to 0, the term does go to 0, then you have to work further. You cannot stop and say that the series converges. That is not true. So now we're gonna study some tests that allow us not to conclude that the series diverges, but to conclude that the series converges. So that is the subject of this section. So we will learn a bunch of tests that allow you to conclude the conversion of a series. So the first test is you have integral tests and comparison tests, and all these work for a special type of series that is a non-negative series. That is a series whose terms are all non-negative. And a special result that work only for positive series is that a non-negative series converges if and only if the partial sum are bounded from above. So suppose that so what it means is that if an are all positive, then this series converge if and only if the partial sum is bounded by n for all n. Now one direction is easy. So this direction we already saw, because if you have a series converse, then the series is defined via the limit of its partial sum. And if you know that this one exists, then that means that the Sn converge. And we know that, I think we proved this, that a sequence converges, then it must be bounded from above and below. So in particular, you have this. Now, how do we go the other way? So why does we have this direction? Why does the boundedness from above of the partial sum implies that the series converges? Anyone knows? Anyone knows why? Remember that we are working with positive series, non-negative series. So all the AN are positive. Anyone knows? So the reason is simply because if you know that, suppose that you have Sn is bounded above by M, and since we are working with a positive series, you see that Sn plus 1 is Sn plus An, and this one positive, so it's bigger than Sn. So the sequence of partial sum is an increasing sequence. And if you know that this is bounded above by M, then by the monotone conversion theorem, Sn's converge. So therefore, this series converge by definition. Is this clear? Any questions? Okay, let's continue now. So to establish the conversion of a positive non-negative series, all you need is to show that the partial sum is bounded from above. So let's try this on this series. Try to see that if you can show that the partial sum of this series is bounded from above. Anyone finished? So for this series, you can compare this with a series that you know. I'm surprised you didn't see this. So Sn here is bounded by, so this is our Sn, right? And so it is gonna get bigger if you omit this part, because the denominator gets smaller. And this one you can compute. You know how to compute this. This 1 minus 2 to the power divided by 1 minus half. And so in particular, it's less than 2. I think I missing a half here, so less than 1. Is this clear? Any questions? Okay, let's take a 20 minutes break then. So see you at 10 to 10. So next we're gonna study the integral test. So again, we are still working with this non-negative series, and if it happens to be the value of a continuous function fx, so an is f at the point n, then if you know further that f is a decreasing function, then you can, instead of working with a series, you can work with the integrals and these infinite integrals here. So the series converge is if and only if the integral converge, the integral of fx. So you need three things actually. So the function f has to be positive and decreasing, and an is exactly the value of f at n. Then you compute these integrals. If it converges, then your series converges. If it's diverse, then your series diverse. But note that these two may exist, but they are not equal. One is finite implies the other finite, but it's not may not take the same value at all. So in fact, here, since for improper integral, this one, instead of taking from n, you can take from any point. You don't have to start with the same index that the series start. You can start at 1, for example. I think there is a slight inconsistencies here. So the series start at 1. So sorry. So this is 1. So you see that you only require that an is equal to fn after some capital N. And this is in the same spirit as what we mentioned earlier, that the behavior of the series, whether the series converges or not, depend on the behaviors of the series at infinitive. So if you change the value of an for finite numbers of n, then it doesn't matter, it doesn't change the fact that the series converges or not. So instead of integrating the function from n to infinity, 1 to infinitive, you can pick any n here. So please try this and determine whether this series converges. You finished? Anyone finished? So in our case, in this example, you can take fx. You see that this is exactly the value of this function at the point n. And this function is certainly decreasing positive, right? And so you try to see if this interval exists or not. So does this converge, this improper interval here? Yes, it's divergent. So you can find its alternative by doing the chain of variable u to be log x. Then this become integral du. So du is dx over x. So this part is du, and you have 1 over u. And so the alternative is log u. See, and log u is log of log x. So you would have so to be, you can write this as log x, and you evaluate from 2 to infinity. Here you think of this as put in a value of b finite, and then you let b to go to infinity. But this is infinity. So this series uh, diverge. And you can also apply this criterion to other the p series that we have earlier. So remember, this is the p series with a power p here, and p is a positive constant, and the special case when p equal to 1, the series have a name that is a harmonic series. And the series we have seen earlier that the series converges if p bigger than 1 and diverges if p less than or equal to 1. And so try to apply this test, integral test, to the p series. So we have saw in the earlier kind of elementary way to prove this. If you want to apply the integral test, you just note that fx equal to 1 over x to power p is a continuous decreasing function because p is bigger than 0. So all you need to figure out is whether this integral exists or not. Now, what is the antiderivative of this? Anyone finish? What is the antiderivative of 1 over x to the power p? So the antiderivative of this is simply you write this as x to power minus p. So the antiderivative is simply x to power 1 minus p divided by 1 minus p, provided p is not 1. When p equal to 1, then the antiderivative is log x. Any questions? And now you see that if p equal to 1, for example, then you evaluate log x from 1 to infinity, and you get infinity. When p bigger than 1, then when you evaluate this from 1 to infinity, since p bigger than 1, this power is negative. So at infinity, this is 0. So you only pick up the 1 at p equal to 1, so it gives you 1 over p minus 1. And finally, when if p is less than 1, then at infinity, you get the power 1 minus p is positive, so at infinity is infinity. So this interval diverges. Is this clear? Do you have any questions? So it gives you the same results as what we obtained earlier. Uh, so let's talk about this remainder estimate. So what we want is to, what it means by the remainder is that if you know that this one converges, so for example, in our case, it will be via the integral test, you compute it and you see that it is converge, so you conclude that the series converges. Now suppose then you know that the limit of the partial sum S capital N here converges to S when capital N go to infinity. And the remainder is the difference when you use Sn to approximate S. So the remainder Rn is simply the difference S minus Sn. And so what we want is to determine how big this error is. So if you know the error of Rn, the size of Rn, then you know that how accurate it is when you use Sn to approximate S. So that is very useful things to have. Now in the case we are working on S's that is f is decreasing, and you can see that you have this estimate for Rn. So Rn lies between these two intervals. So um, this is a different thing. Yes. So Rn here is so you can think of Rns as, so this may be easier for you. So Rn is S minus Sn, and you can think of this. So S is the sum from say 1 to infinity, and Sn is from 1 to n. So Rn is a sum of n bigger than n. So maybe that is also why they call a remainder. Right? So all the so this sum of n bigger than capital N. Then if you use this expression, then you can see easily why we have this inequality. So let's see why this is. Okay, so here we have n instead of capital N, but it's that's a minor point. So think of this as capital N, okay? So this sum you can think of as the area of all these rectangles here. So the base is always 1, and the height is equal to the height here. Since this is a position n plus 1, it is exactly an plus 1 here, because this is an plus 1 equal to f of n plus 1. So this is exactly the height. And the area of this rectangle is equal to an plus 1 because the base is 1. And similarly, the next one, the area is an plus 2. Now, if you convert to area like this, it's very easy to establish this inequality, for example. Because now you can see that all this area, the region bounded by this rectangle, lies inside this part. So the area under the graph of f between n to infinity, and that is this integral here. So by comparing these two areas, you obtain this estimate. Now to get the other estimate, this one here, what you have to do is you don't see here you have draw the rectangle. You pick the point, say n plus 1, and you draw the rectangle to the left. And the same here, so you look at the point n plus 3, for example, you get this height, which is an plus 3, and you draw this to the left, then it's going to be under the graph of f. Now, instead, if you draw the rectangles to the right, then it's going to lie above the function f because f is decreasing. And so the sum of this area is still equal to this sum. But now it lies above the graph of f, so it's bigger than the integral, the area of this region here. And so it's bigger than the integral from n plus 1 to infinity of fx dx. So this is why you have this. Is this kind of clear, or do you have any questions? Is this okay? So let's just do one example here. So let's say you have the sequence sigma 1 over n square. Okay, maybe let's call this j. Just so it's not confused with. So you know that this converges. This is a p series with p equal to 2. So it's going to converge to some value, say L. Let's call this S. So how big do you have to take n so that the difference is less than, say, 10 to the minus 6? So suppose that you want to have these accuracies. So you know that this is always positive because there's a series of non-negative terms. So suppose that you want to approximate this S within 10 to the power minus 6. Which n can you stop? The bigger n is, the better the approximation. But what is the smallest n that you can take so that you have this bound? For which n here? Can you try this? Anyone finished? Let's see. Okay, please try. So just remind you that this one is exactly Rn, and so since we want this bound, so this is Rn here. You would use this inequality. You finished? Anyone finished? So for this, you simply take f. So fx in our case is 1 over I squared. Right? So because of this inequality, all you need is to find an n so that this integral is less than 10 to the power minus 6. So you want the value of n so that this one less than 10 to the minus 6. But the antiderivative of this one is simply 1 over x. And when you evaluate from 1 n to infinity, you get 1 over n. So what you want is this one less than 1 6. So n need to be bigger than a million. Is this clear? Any questions? Okay. Okay. All right. So this is a very important estimate. So let's talk about the comparison test. So we seen a kind of this test earlier. When we do this, remember here we show that because of this theorem, we show that S is suffice to show that Sn is bounded, and we prove this. And during the proof, what we did was you replace Sn, the term here, by these terms. So the spirit of this is actually we find a series whose terms are bigger than the one that we want to study, in such a way that this new series is easy to compute. In our case, this is a geometric series. So that is one instance of these comparison theorems. that we have next. So if you have a positive series and an is always less than bn, then the bigger series converse implies a smaller one converse, and the smaller one diverse implies bigger one diverse. So certainly, if you establish A, then A imply B, right? Certainly A imply B, because if B is fail, that is you have A divergent but B is convergent, then by part A, uh, the sum of A and is also convergent, and these two are contradiction. And the proof of this is very simple, because you know that um, this one converges if and only if the theorem that I just mentioned earlier, the partial sum is bounded, right? So you just need to establish a upper bound for this partial sum of an to show that it's converged. But we know that this one is always less than bn, and in particular is less than the infinite sums. And this is a finite number because bn is convergent. So this one has an upper bound, so therefore the sum of an converges. So very simple observation, but it allows us to make a, instead of studying a complicated series, you can instead look at a simpler one. So let's do this. Let's try this example here. So which one converges? You finish which one's conversion? Anyone finished? Okay, let me show you how to do this then. So first, let's notice that we only need this inequality to hold for large n. So this is in the same spirit that I mentioned earlier, that the series converse. The conversion of a series only depend on its behavior at infinitive. So for this series, you can check that log n over n is bigger than 1 over n if n is bigger than 3, right? Because e is less than 3, so n is bigger than 3, then log n is bigger than 1. So this is a bigger one, and the smaller one, the small series diverge, because this is a harmonic series p equal to 1. So this one diverge, that implies that this one diverge. Is this clear? Any questions? For the second series, you simply notice that 1 plus sine n of n squared is less than 2 of n squared. And now this is a p series with p equal to 2, so it's converged. So the bigger series converge implies that this series, the smaller one, also converges. If you have questions, let me know, right? So let's just do one last example about this. So this is very similar to what we did before, but what happened if I have this? Does this converge? Have you finished? Yes, it's a conversion, and but the difficulties is now that is unlike the previous one. We have if you have plus sign here, it's very easy, and this is lesson. You can do this. But if you have the minus sign, then it's unclear whether you can do such a thing. And so the key point is uh, remember that the exponential powers 2 to the n grow faster than any polynomials. Remember we maybe it's in analysis 1. I don't remember this. So if so for example 2 to the x to the n is infinity for all power n here. So exponential grow, the powers grow very fast. Yes, it's exponential here, grow faster than any powers of x. So it would be so much faster that eventually it's gonna be, so because of this fact, you can, prove this by L'Hopital. You can try L'Hopital on this and you can see that, let's say we do this for number 2. So eventually for large, let's say n bigger than capital N, this will be very large, and in particular it's bigger than say 4, and then you can simply multiply here. So that implies that 2n minus n squared is bigger than n squared, and when you flip it, you have less than 1 over n squared. And so this is a p-series that converges, so this one also converges. Any questions? So in fact, the principle, the bigger one in between these two guys is 2 to the n. So the series was pretty much still pretty much close to this series, and precisely what it means by close is make clear in the following limit comparison test, which you can use instead of this. So this is limit comparison test. Oops. So if you know that the quotient an bn converge to some finite number that is positive, so it's very crucial here that it's positive, then either both converge or both diverge. So try to establish a conversion of this. So you need to find a bn so that this one divided by bn converge to some finite number k, and the series bn also converge. So can you tell me what's bn should be taken here? So what should we take for Bn? So which Bn's would have essentially the same behavior as this one? Anyone knows? So what should we take for Bn now? So no one knows? So for Bn, you can take 1 over n squared because essentially all these terms are small compared to this, and all these are very small compared to this, in the sense that the ratio go to 0. So essentially this one behaves like 2 to the n squared over n to the power 4. So if you take Bn to be 1 over n squared, then you see that An over Bn converges to 2 over 7, which is a positive number. So you need it a non-zero number. And so if you have and if you look at sum of Bn, then you get this P series with P equal to 2, so it's conversion. So by the theorem, this the original series also conversion. Is this clear? Any questions? So that is essentially the two tests that we have that is special to positive series, that is a comparison test and integral test. Now we're going to study a test that work for series that have negative terms. But this the series that we're going to look at is kind of very special in that the sign are alternating. So you have one positive term and then negative and positive, negative, so on. So we require that our series has this property that an and an plus 1 is negative for all n. So that the signs of an and an plus 1 are opposite. Then for this series, we have a very important theorem which says that if you have this and also the size of the terms go to 0 and decrease to 0. Not only it has to go to 0, but it also have to decrease. then the series converge. So for example, both of these conversion. This you already know because this is simply a geometric series. But this one you see that if you take all the plus sign here, then the series diverges, right? That is a harmonic series. But now if you change the sign for every other terms, then what you get is a convergence series. That is the content of the alternating series test. So for an alternating series of this form, so let's assume that for definite, you assume that the first term is positive. So you have a C1 here is positive, and then negative, and so on. And now suppose that the size of the terms is precisely these Cn's. And if you know that the Cn's that are decreasing, so that is condition 1 here. The second condition is that the size go to 0. Then this series converges. And furthermore, you have an estimate for the remainder. You see, this is exactly n that we defined before. But remember, now our series is not a positive series, non-negative series. So this is the absolute value of the remainder term. So this can take positive or negative value. So if you stop, for example, if you take this, so this gives you S4, right? If you stop at 4, then the value of the whole series minus S4 is less than the next term, so that is C5. So is this clear? The statement of the theorem is clear? Okay. Right. So I'm not sure if I should, maybe I give you, okay, let's see. Yeah, so one example is a harmonic, alternating harmonic series that we already see. And more generally, you can look at the alternating P series. So without this sign factor here, this one here, you would get, if you don't have this, you have just one, then that is a P series. Now you put in the alternating sign, then you get the alternating P series. Then this series now become convergent for all P bigger than 0. Before, for the usual P series, you need P bigger than 1, right? But now you put in the alternating size and suddenly it's converged for all P positive. And the reason is this function, the size of the coefficient go to 0, decrease to 0. And so by the theorem is convergent. And not only that, so alternating series is it's always when you have this negative sign, there's a lot of cancellation going on, and it makes the series converge. So here's the proof of the alternating series. So so what you do is you're looking at the sequence of the partial sum, and you want to prove that it's converged. So this is kind of very similar to one of the examples that we have earlier. And we have the continued fraction of I think square root 2. I think we what was that sequence? I forgot. I think we did this sequence when you start with a1 is 1, and then you get something like this, if you remember, and you we establish that this sequence converges. And what happened with this sequence is that it's not a monotonic sequence. But if you pick out the even terms, the even subsequence and the odd subsequence, and one of them increasing, the other decreasing, and you can use the monotone conversion theorem for the odd and even sequence and establish conversion from that. And something similar happened here. In that the sequence of the Passer sum is not monotonic. But if you look at the odd and even terms only, then you have a monotonic sequence. So you remember you start with C1, which is positive, and you have this. Now this is for this series, you can show that the even Passer sum increase and the odd Passer sum decrease. And you can see that easily from this fact here. So let's say this is S4. Well, let's work on in general terms. So S4, I think there are some mistake here, but yes. So S2K yes is 2K plus 1 is C1 minus C2 plus C minus C2K plus C2K plus 1 minus C2K plus 2. And you notice that here is S2K. And because of our condition, the sequence Cn decreasing, so this is positive. So that implies that S2K plus 2 is bigger than S2K. And similarly, you can show that S2K plus 1 is the sequence of odd Passer sum is decreasing. So you have this type of inequalities. So the sequence of my even increasing and is always smaller than the sequence of odd Passer sum. So each has a limit. And you can see that if you look at this difference here, the difference of these two limits is equal to the limit of C2K, which is 0. So the whole sequence of Passer sum converge. So this is very similar to the problem that we earlier. You establish the conversion of each subsequence, then shown that their limits are the same, and so the full sequence converge. Okay. Any questions? And from the proof, you can see that if you look at this, the difference here, the error here is less than Sn plus 1 minus Sn. Because, well, you can see that from this, the odd member is always bigger than the even one, and S is something in between. The limit of the whole thing, the value of the series, has to be in the middles. So the distance with S each of these is less than the next term. So let me not going over that. Just So, and this is exactly Cn plus 1. So let's try this example. So how big should n be so that the error using Sn is less than 10 to the power minus 3? So if you want this error less than 10 to minus 3, then you would you need the next term. So the next term is 1 over 2 to the power n plus 1 less than 10 to the power minus 3. So you need n bigger than 9. Okay, so let's go back. So remember, for this series, we have shown that if n is bigger than a million, then Rn is less than 10 to the power minus 6. Right? We use the remainder estimate for the interval test to prove this. Now for this series, so the alternating version of this one, what should we put n? How big should n be so that you have this less than 10 to the power minus 6? So please try this. So have you finished? So how big should n be so that the remainder is less than 10 to the power minus 6? Anyone knows? Well, so you can just do the following. You can um, you just use the estimate, right? So S Rn is S minus Sn, so it's less than the next term. But the next term in the series is this one, right? So if you want this, you simply need n plus 1. You need n plus 1 bigger than 10 to the power 3. So you can take n bigger than or equal to 10 to the power 3. Is this clear? Any questions? Any questions at all? Okay, so you see that for this series with all term positive, you take n has to be very large to have this accuracies. Whereas for this alternating series, with the same accuracy, you only need this n to be this big, so which converges much faster than the one with all the positive signs.